real-time OS and the avenues of research and development for a real-time application and what they're being used for and how they're being pursued. So our first topic is the definition of a real-time system, which is a system that handles events as they occur, responding in a correct and timely manner. Real-time systems are used in the manufacturing, telecom, health, transportation, and numerous other industries. And the two types of real-time systems are soft and hard real-time systems. A soft real-time system is one where deadlines don't have to be met all the time. They can be met a majority of the time or on average. And this is usually the case with things that don't threaten life or aren't really that catastrophic if you miss a deadline. So I have a photo of the Netflix logo, and that's to illustrate a soft real-time system. You know, in the worst case, if a deadline's missed on Netflix, then you drop a few frames or your video pauses or crashes in the worst case. And that's a soft real-time system because on average, Netflix meets its deadlines, and that's why your video works. For a hard real-time system, I guess a perfect illustration is the system that's in your car for airbag deployment. The deadline to deploy your airbags must be met every single time, or in this case, for most cars, only once. But once that interrupt is received and that deadline is created to deploy your airbags, they have to occur on time. Our next topic is the definition of Linux, and it's an operating system derived from the Unix operating system. It has a very, very large array of flavors and functions, and it's mostly designed for general purposes. Linux generally is a single or multi-user operating system, but it can be adapted to handle real-time systems as well. The Linux kernel was created by Linus Torvalds, and Linux is an open source OS. So common flavors of Linux include Ubuntu, Debian, Red Hat, and Tails, along with numerous others. The illustration to your left actually is a display of, I guess, many Linux flavors commonly available. Ubuntu is a common desktop operating system or PC operating system, as is Debian and Red Hat. And Tails is an operating system that is closely associated with the whole Tor network sort of browsing. It's focused primarily on privacy. Implementing Linux as a real-time OS. So there are four main ways of doing this. Three are declared on the screen, and then the fourth one isn't listed, but it's basically using the stock Linux kernel with small modifications to make it handle soft real-time systems. So we'll start with that. The stock Linux kernel in Linux 2.6 can handle soft real-time systems if you enable full preemption, which means that it will know the priority of a task, so to speak, and it won't let lower priority tasks happen before higher priority tasks. The next means of implementing Linux as a real-time OS is through the use of a thin kernel, which sits above the hardware layer and catches all the interrupts for real-time tasks. And catches those before the original Linux kernel can catch them, and that enables, hard real-time system handling, or hard real-time system creation rather. And then the thin kernel and the original Linux kernel are basically separate. So the original Linux kernel handles user type interrupts, and then the thin kernel handles real-time systems, or real-time system interrupts, excuse me. The advantages of such a system are that it's excellent at handling interrupts very fast. And the disadvantages are that debugging is a complicated task. Real-time tasks and other tasks are completely separate. And an example of the thin kernel system is RTAI, or the Real-Time Application Interface, and ZenMI. Our next means of implementing Linux as a real-time OS is the nanokernel, which is basically multiple kernels sitting above your hardware, and that creates a hardware abstraction layer, essentially, and it allows to prioritize tasks. So when an interrupt is received, the nanokernel actually senses which kernel or which operating system, in the case of multiple operating systems, which can be handled by the nanokernel, would best handle that interrupt. And the advantage to that is that it can prioritize tasks. And then an example of the nanokernel is the adaptive domain for operating systems, or RTOS. And then finally, there's the resource kernel, which basically shares space with the original Linux kernel, but it's a small bit of code appended to that kernel, so it allows Linux to handle real-time system tasks. And then advantages of that system are that it guarantees access to the entire system, as opposed to a thin client or a thin kernel. as mentioned above, and it can accomplish for the task that it can accomplish. So it's not guaranteeing it can accomplish all of them. So therefore, the resource kernel would not be good for a hard real-time system, but it does guarantee full access to all system resources for those tasks it is going to accomplish. And an example of that is Linux/RT. On this slide, you see the 4 diagrams of the 4 Linux kernel approaches for real-time systems that I mentioned previously. The resource kernel, as you can see, kind of has a small green rectangle representing the resource kernel inside of the Linux kernel, kind of showing that it doesn't take much of an alteration to implement a resource kernel type of alteration for the Linux system to become a real-time OS. And on the other end of the spectrum, you see the nano kernel, which has multiple other kernels attached to the original Linux kernel, and that's split for multiple operating systems or multiple tasks, or just to run multiple higher level things above the interrupt dispatcher and the nano kernel. And then the thin kernel is essentially separate from the Linux kernel itself, as you can see by having a hardware layer, then the thin kernel, then the Linux kernel itself. And then to the right of that, you see the Linux kernel itself, which is basically representing when you enable preemptible mode for that Linux kernel to allow for soft real-time performance. The common real-time Linux flavors are preempt RT, which is a patch, and a patch basically is it's almost like a resource. It's almost like the resource kernel implementation, to where the original kernel is patched to allow, I guess, higher level tasks or real-time tasks. It's patched to be more adaptive to those tasks. Linux RT is a resource kernel implementation. RTOS is a nano kernel implementation. RTAI is a thin kernel implementation, and the same with ZenMI. And I guess put simply, real-time applications of the Linux OS are performed through patching the normal Linux kernel or creating a subkernel. And then advantages and disadvantages of Linux as a real-time operating system. Advantages is that it's open source, it's stable, supports multiple processors, and it's adaptable. And it can also support hard and soft real-time operating system options, depending upon how you implement the Linux operating system as a real-time system. So if you implement a thin kernel, then it can handle hard real-time OS applications, versus if you only use the Linux stock kernel, but you enable preemptible mode, then it'll run as a soft real-time system. Disadvantages. The kernel in the OS must be modified to handle real-time systems. Linux right out of the box will not handle real-time systems unless you either enable preemptible mode or you append or change the kernel in some way. Real-time applications can crash the machine. These disadvantages, this one and the next 3, are only for patched kernel options, like the preempt RT patch and things like that. So they don't quite apply to all the other ones, but I suppose anything can happen. So real-time system and user system can't communicate in real time with a patched kernel, and Linux is slowed by the real-time tasks. Also, drivers can't be shared, and like I said before, these are all for the patched kernel. See my references, and I appreciate y'all listening to my discussion of Linux as a real-time operating system, and I hope you have a wonderful night. Thank you.